my name is Sham Rampersaud. I am a PhD candidate in Arun Weeda's lab, and I'm here to tell you about engineering best-in-class CAR T therapies to treat acute myeloid leukemia. Acute myeloid leukemia is a disorder of the bone marrow characterized by malignant expansion of undifferentiated myeloid progenitor cells, which crowd out the marrow and cause bone marrow failure. AML is diagnosed in greater than 20,000 Americans per year and has generally a dismal prognosis with only a 30% 5-year survival rate. The field has made tremendous strides in defining the molecular landscape of AML, which has significantly impacted what we can offer as a standard of care, including targeted therapeutics. However, the median overall survival is still modest and has remained relatively unchanged. The only curative modality is high induction chemotherapy followed by stem cell transplant. This is never simple, as this graph highlights, as not every patient meets eligibility criteria for chemo or transplant, and so additional modalities are needed, such as immunotherapy, which is the type of therapy I'm interested in designing. Now that you're aware of the dismal landscape regarding AML standard of care, this provides a perfect platform to develop cellular therapies, or in my case, chimeric antigen receptor T-cell therapy. This involves engineering a patient's own immune cells to target disease. In previous attempts to apply CAR T therapy to AML, top clinically tested targets include CD123, CD33, and CLO1, but their major issue is that they share expression on healthy hematopoietic stem cells. Not only are you wiping out blasts, but you're also wiping out the healthy marrow in these CAR Ts. Primarily, failure in CAR T therapy is due to failure to control disease, in addition to on-target off-tumor toxicities. And so why do CAR T therapies in AML tend to fail or fail to control disease? It is due to a number of reasons, such as antigen escape, on-target off-tumor toxicity, tumor heterogeneity, and immunosuppressive cells that block therapeutic T-cell function. In my approach to mitigate these issues, I aim to incorporate two blast-specific antigens, active integrin beta-2 and CD70. Both are tumor-specific antigens. I aim to overcome the immunosuppressive microenvironment by incorporating the most potent T-cell modification known in nature, the CAR11-PIK3R fusion. To test our new CAR Ts in controlling disease, we utilized an AML xenograft model and showed here that the CD70 and active integrin beta-2 CAR Ts are able to display robust tumor control. Additionally, the enhanced active integrin beta-2 CAR T is able to extend overall survival in preclinical mouse models by 180 days, or a number of decades in human life equivalents. Furthermore, we tested our CAR T in mice with full immune systems and showed that we had potent tumor control. Finally, in my research, I aim to develop a best-in-class AML CAR T, but I also aim to study mechanisms of CAR T resistance in AML using immunocompetent AML mouse models. And I want to thank the ARCS Foundation for supporting me in my research endeavors in developing best-in-class AML CAR T therapies. And I also want to thank you all for listening to my research so far. Thank you very much.